organizing this nice conference, and I'm very happy to give a talk. So we'll speak about the standard conjecture of Hodge type, and here's the outline of the talk. So it's 4 parts, and I would like to start with the classical case, which goes back to the 30s. It's about surfaces. And then I will give the statement of the conjecture from the 60s, which is due to Grothendieck and Bombieri. And then in the last 2 parts, I would like to explain the strategy. First of all, with the toy example, the Fermat cubic fourfold, and then I will discuss about abelian fourfolds. Okay, so let me fix some more or less standard notation. So I will always work with smooth projective varieties over a base field K. D will be the dimension, and I will need to fix an hyperplane section L. And I will only work with the numerical equivalence, so this may be not always standard. So I will just write Zn for the Q vector space of cycles modulo numerical equivalence. So it's a finite dimensional Q vector space, and rho n will be the dimension. Okay, so let me do a little summary, and let me now properly start. Okay, so let me start with the theorem from the 30s, which is due to Hodge over C. And which is due to Segre over a general field. So here, let me take dimension 2, and X I will just write for psychological reasons S. And the statement is the following. So the intersection product so let me call it P, which take divisors, so curves over the surfaces, and counts the number of intersection points. So this intersection product is of signature the following. Oops, sorry, I'm not very comfortable with this. Oh, sorry. Is it readable?
Okay.
Okay, sorry. So the intersection product has the following explicit signature. So 1 is positive, and all the rest is negative. Okay, so this is the statement. Okay, let me give some remarks. So first of all, if you take an hyperplane section, the intersection product is always positive. This is some classical positivity property of ampleness. You can also see it geometrically. If you take 2 hyperplanes, you can choose them with Bertin in order to intersect the surface transversely in a positive number of points. Okay. So this is somehow easy, and the real content of this theorem is the rest somehow. So it's equivalent saying that P restricted to the orthogonal part of L is negative definite. So it's a negativity statement to the theorem above. And second, so if you now take C, this is the theorem of which was first proved by Hodge. Here you can use the following. You can use a cycle class map and see divisors inside cohomology. And it goes here, and here you can reduce the statement to the signature of cohomology of the cup product. And okay, somehow the paper of Hodge from 33 actually shows what is the signature of the quadratic in this case, and nowadays we just call this kind of signature properties the Hodge-Riemann relations. Okay. Okay, and as this is a workshop on Weil conjectures, let me recall why Grothendieck got interested in this statement. So if you apply the above to S equal C cross C, and here you take a base field, a finite field. So you have a negativity statement on divisors on S, and you apply these negativity statements to the following divisors on C cross C. So you take a vertical divisor, an horizontal divisor, the diagonal, and then you take the graph of the Frobenius. So you take these 4 divisors, you apply the negativity property above, and you deduce the Lang-Weil estimates, which is equivalent to Weil conjectures for curve. Okay. Okay, and the result I would like to present today is the following. So take an abelian fourfold. And the interesting case is in positive characteristic. Then the intersection product. Now we take surfaces over the abelian fourfold, and we count the points of the intersection. Then this intersection product is of signature an explicit formula. Okay. So somehow the negativity part is precisely the same as the theorem in the case of is exactly the same that appeared for surfaces. So somehow the negativity part is coming from divisors, and you should think of this statement as a positivity result. Somehow all the rest is actually positive. And okay, so we'll explain in a few moments. This statement is precisely equivalent to the standard conjecture of Hodge type. Is just a more direct formulation. And let me give also a corollary. So you need to use this theorem together with a theorem of Clausel. And you deduce in the following. So you fix an abelian fourfold. A, and then there exists infinitely many primes such that numerical equivalence on A is the same as homological equivalence for the L-adic cohomology. Okay, so this is also one of the standard conjectures. So what is basically missing in order to understand all the standard conjecture for abelian fourfolds is exactly to understand the L-adic independence of this relation here, which is unknown, which is still open. Okay, so this is somehow an introduction of the question. Are there questions so far?
These numbers in the signature, what are these row 1?
Sorry. So this is sorry, I should have recalled. This is the convention I used here. So row 1 is the dimension of divisors, and row 2 is the dimension of codimension 2 cycles. Okay. So here, what I'm saying is that some of the negativity part is just the same formula as for surfaces. So the negativity part is coming from divisors. And some of the real statement is that the rest is actually positive. Okay. I don't know if it's clear. More questions? Okay. Let me now recall the statement of the conjecture. So we take the following definition. I take a degree at most half of the dimension of the variety. Let me first define the primitive part. Maybe I'll inside this. So these are classes such that when you intersect with the hyperplane section enough times, then you get a zero class. So if you see this for the first time, this may be a bit strange. This index, and the point is that it is the first index where this intersection has any chance to have a kernel. Okay, if you intersect with less power, then the only alpha which would have intersection 0 would be actually alpha equals 0. So this is the first operator, the first Lefschetz operator which has a kernel. That's the primitive part, and now let's define a quadratic form on this primitive part. Okay, this is depending, of course, on L. Also, the primitive part is depending on L. And the definition is the following. So it's pretty similar to what we did in the previous theorem. So we just take the intersection. But if you just take the intersection, of course it's codimension 2n, so it's not a number. In order to obtain a number, we iterate the intersection with L. Now it's a number of points, so we just consider this number, and then we slightly change the sign. It will be clear in 1 second why, but if you remember in the theorems I gave in the first part, in the case of surfaces, it was a negativity theorem, and in the case of fourfolds, it was a positivity theorem. So this sign is now correcting this in order to have always a positivity statement. So let me give an example. So if I take a surface, now you can consider curves on it, and we are just taking the line generating by an hyperplane class, and it's orthogonal with respect to intersection product, and this orthogonal is the primitive part. So it clearly depends on L, and so the theorem of Segre, which I gave in the first part, we saw that it was equivalent, saying that the intersection product restricted to this orthogonal part is negative. But now we change the sign, and so this is equivalent, saying that Q1 LS is positive. Okay, so that's why there is this correction. Okay, and I think with this example in mind, you can guess what the standard conjecture of Hodge type should be. The statement is that Q and XL is always positive definite. Okay. So let me say what is known. Okay, so first of all, the case of divisors is known. And this comes from the following. You can construct a surface inside X, taking different hyperplane sections, so by Bertini, so it's still smooth and projective. And then with Lefschetz, when you construct such a surface, with Lefschetz will tell you that pulling back divisors will be injective. And you need to check that this is compatible with these quadratic forms, but it is the case. And so you can conclude using the positivity here. Yeah, so it is here by Segre, and then you deduce positivity here in general. Okay. So the second case, which is known, is the case of characteristic 0. Here now you can use the class cycle map. And it will go inside H2n singular in the NN part. Also a very important H2n primitive part. So there is also an analogous definition of primitive part in cohomology. And because of the definition, it is respected. And here again, this is a Q-vector space. So it makes sense to look at the signature there of the cap product. And that's precisely what Hodge-Riemann relations do. So here we have positivity because of Hodge-Riemann relations. Okay, so these two cases, as you can see, are rather classicals, and these were actually the motivations of Grothendieck for believing these were already known to Grothendieck, and these were the motivation for believing the conjecture. And since the 60s, there has been two sporadic varieties for which this conjecture has been shown. So the first is from Tate. I think it's a letter of Tusser in the 70s. And it shows the following. So if you take a finite field, and if you take a Fermat of this very special degree, of this precise degree, so q plus 1 in dimension, this has to be even dimensional. Then the conjecture is known for this variety, and it's a very beautiful argument using groups acting on cohomology. And the other case which is known is the theorem of Ito. I think it's the same Ito as in the first talk. So it's now 2005, and he showed the conjecture for some blow-ups of Pn along some other linear subspaces. So in particular, the cohomology is algebraic. So even in this very special case, the conjecture is difficult. Okay, and okay, so the last case, which is the one I would like to talk about, is the case of abelian fourfolds. And the statement of the standard conjecture of Hodge type, if you somehow look closely at the definitions, it's precisely equivalent. So this primitive part and this quadratic form, it's precisely equivalent to the statement I gave at the beginning. Okay, so this is a little summary. Are there questions so far?
For this case, I guess for this case two, this cycle class map, you are going to take the homological equivalence, not the previous numerical equivalence, right?
Sorry, I can't hear you clearly. Can you say it again?
So in this case 2, incorrect characteristic 0, so because incorrect characteristic 0, we don't have a standard conjecture D. Then this Z case, you need to take modular homology.
Yes. Okay, so yeah, so Thank you. I was trying to hide this point, but let me say that I'm slightly cheating. But so what you really need to do when I say class cycle map is that you should consider this. This goes to cohomology, and you should consider this quotient to numerical equivalence. And when you study this diagram closely, you can do all the arguments I gave. So in reality, I was kind of cheating by saying that there is such a map, but there is not such a map. But you can go around. There are sections here you can which respects the intersection product. It's a technical detail, but you don't need a conjecture D in order to do these arguments. Okay. Okay. More questions? Okay. Okay, so now I'd like to explain the strategy. Let me start with my baby case, which is the Fermat cubic fourfold. So you don't really need to know the geometry of this guy. What is important are the following cohomological facts, which are, I think, all of them due to Shioda. So first of all, let's start over C. And of course, what is interesting is the middle cohomology. And this is an Hodge structure, and the Hodge structure is the following. So there is Tate type, which appears 21 times. And then there is a small rest, which I call VB. And this is an orthogonal decomposition. And VB is a two-dimensional Q-Hodge structure. Sorry, Q-Hodge structure, which is two-dimensional and which is of type 1331. Okay, so there is a lot of 2-2, and then there is a little Hodge structure more. Second, the Hodge conjecture is known. So in particular, the cycles of codimension 2 is a 21-dimensional Q-vector space. And the class cycle map, I'm defining an isomorphism of this guy with the 2-2 part here. Okay, so this is over C. So basically everything is algebraic except a small two-dimensional Q-Hodge structure. And now we go over FP bar. And here, of course, we replace all this with the Alladic cohomology. So here, the Alladic cohomology. So I just write L for the Tal cohomology in QL coefficients. And by general theorems of on Alladic cohomology, we can compute this from singular cohomology of the lifting to characteristic 0. And this comparison is compatible with a lot of things. And in particular, we need them to be compatible with the intersection products and the camp products. So all the quadratic forms we will consider can be computed on the left or on the right. And the other thing we need to do is know is what about cycles? So when P is 1 modulo 3, then there are no more cycles than those coming from characteristic 0 by specialization. So it's 21-dimensional. And the interesting case will be when you go now for the other primes. And here, this guy will be bigger. It will be 23-dimensional. So in particular, it will span the cohomology. Okay. So with these facts in mind, I would like to explain the fact that the standard conjecture of Hodge type holds for this variety in all characteristic, and of course this will be interesting for these exceptional primes, the super singular primes, because of course in characteristic 0 we saw that the standard conjecture is known, and for as long as all the cycles are coming from characteristic 0, this is also deduced from characteristic 0. Okay, so the interesting case is here. And so more precisely, we need to study the following space. So the orthogonal part of cycles coming from characteristic 0 inside those from characteristic P. Yeah, so from now on I'm taking the primes with more cycles in characteristic P. So this is a two-dimensional Q-vector space, and I take this quadratic form to be the intersection product. Sorry, intersection product restricted to VZ, and the goal of this proposition, of course, is to show that QZ is positive, definite. Okay. So we understand everything coming from characteristic 0, and if we want to show positivity, what is missing is exactly this orthogonal part. And in order to understand it, we will use another quadratic form, an auxiliary one, which will be the cup product on VB, so the Hodge structure I defined before. And what is really important to keep in mind is that these two quadratic forms are Q quadratic forms of dimension 2. That's the most. This dimension 2 is very important. Okay. So I will explain the proof in 1 second. If there are no questions on this background on the cubic fourfold. Okay, so let me explain this. Okay, so the goal is to show that the intersection product on characteristic on positive characteristic is positive, so QZ is positive. But let's first start with QB, so the cup product, and this is negative because of Hodge-Riemann relations. So it's not it does not have the good sign. Because I recall that it is of type 1331. So that's the reason why the change is not a good one. Okay, so somehow QZ and QB, they must be different. That's the idea. On the other hand, for all L different from the characteristic, they are the same. So why is it so? So take these two spaces, VB tensor QL and VZ tensor QL, and we look at them inside the L-adic H4. And so one is by definition the orthogonal part, the orthogonal of the 2-2 part. And the other is by definition the orthogonal of cycles coming from characteristic 0. But these two are the same. Okay. And as I explained, all these identification are compatible with all the quadratic forms we are looking at. So this shows this equality. Okay, so general theorems on L-adic homology will give you that they are the same tensor QL for all L. And you can deduce from there that QZ is positive definite or negative definite. And the reason is that, let me explain this. Okay, and the reason is that they have the same discriminant. Discriminant of QB, tensor QL, is the same as the discriminant of QZ, tensor QL, for almost all L. And this implies that it's the same over Q. Okay, so this was of signature 0,2 by the original relations, and this must be of signature 0,2 or 2,0. And of course, we would like to exclude this case. Okay. So the goal now, so there are these two possibilities. Either is positive definite, either is negative definite, and we would like to have something that tells us what is which case is it. And this something is the Hilbert symbol. So the goal is to show that the Hilbert symbol of this quadratic form at the real completion is 1. Okay, let me recall that the Hilbert symbol is equivalent, is by definition the fact that it's 1 when there exists a solution. So this is the very definition of the Hilbert symbol to this kind of equation. Okay, so this is over the reals is precisely making the difference between being positive definite or being negative definite. Okay, and this Hilbert symbol makes sense over any field, and it's particularly interesting law. Let me explain. Okay, so now let me say that this goal is to the fact that QB tensor QP is not isomorphic to QZ tensor QP. So that's the key point, because we are now translating a signature problem into a p-adic problem. As I said at the beginning, these quadratic forms cannot be the same because this one is negative definite and the other one should be positive definite, and they are the same over all L. And now the point is that we need to distinguish them over the p-adic completion. Okay, so let me explain why this is the case, why the goal is really equivalent to this. And the point is to use a product formula, which is classical for Hilbert symbols. So we take the product of all Hilbert symbols for QB at the different completions. And this product is always 1 for all quadratic forms. So that's the same for the other one. But we can now simplify all L because they are the same over all L. Simplify all L different from P. So we just simplify all this and we get something like this. So the B at P and the Betty, so the singular cohomology at infinity, it's the same as these signs, ZP and ZR. And so the original relation told us that this is the sign here is -1. It's negative definite, and the goal is to show that this is +1. But in order to show that this is +1, it's exactly the same as saying that these two signs are different. Okay, so that's the proof. That's why we need to distinguish these two quadratic forms at the p-adic place. Okay, and the final step, let me explain why they are different at in the p-adic place. So QB tensor QP is not the same as QZ tensor QP. Let me explain why. So first, there is theorem of Faltings, 89, which is the most important theorem in p-adic Hodge theory, that tells you that these two quadratic forms, exactly as above, they become the same if you tensor with one of Fontaine's ring. Should imagine this as the comparison between singular cohomology and the RAM cohomology, for example. And the point is that the matrix sending one quadratic form to the other is computable. This. And when you compute it, you can, for example, check that the two quadratic forms are not representing the same elements over QP. So they are not isomorphic. Okay. So let me just give a silly example in order to understand the kind of argument we're doing here. So imagine you have two quadratic forms over the reals. It's over the reals. And suppose you don't know them, but you know that they are isomorphic tensor C. So somehow the decrease here is becoming C. And suppose that you know, for example, that the isomorphism between these two quadratic forms over C is given by the following matrix. Okay, then even if you don't know Q1 and Q2, just the fact that the matrix is this one, of course, will give you that Q1 is not the same as Q2. Okay, and that's precisely the kind of argument which is happening here. Once you explicitly compute this period matrix, you can deduce that they are not the same over QP. Okay, so the main ideas are.
Question.
Yes.
Yeah. So you mean that if the matrix is with some coefficients not in C, then they are not the same, or right? Not in real numbers, not in R, then Q1. In your example.
Okay, so the question is about the example. You want me to explain why what I'm saying is true?
I mean, so you mean that if the matrix is has some coefficients not real numbers, then they should be different, right? That's what you mean.
Wait a second. Here in the example, sorry. Okay. So your question is about this example, and what I'm saying is that what I'm saying is that if the base changes this matrix, then you see the signature is changing because of this I, and then they are not the same. And this, I don't know if the question is about this example. I couldn't hear you very well. I don't know if the question is about this example or about how it does apply in the p-adic case. I'm not sure.
Just about the example. Okay, so you mean okay? So if you look at the matrix, then it changes the size. Okay. So yeah,
exactly. If you know that the matrix is this one, it's changing the signature, so they are not isomorphic.
Okay, I see.
So the point of this example is that even if you don't know these two quadratic forms, just the fact that you know the period matrix, this base change, it's enough to understand that they are not the same over R. Okay.
Okay.
And the argument here is precisely the same, just with the bigger ring and with, but it's exactly the same. You see, you need to know that this base change is a little bit compatible with the Yeah, okay, maybe I don't want to go into details. Okay, I don't know if I answered the questions.
Yeah, it's good. Yeah, yeah. Thanks.
Okay, okay. Are there more questions? Let me. So the main argument and the main idea is really here in this page. The point, the only thing we really used is that these are quadratic forms of rank 2. And as soon as you have quadratic forms of rank 2, you look at invariance locally, and you really translate the problem into a p-adic problem, and there it can be solved. It's well known that in characteristic P, you don't have a cohomology with the real coefficients. And here the idea is that, okay, instead of using cohomology in real coefficient, we can use all the other coefficients, all the other completions, and the product formula will give us the answer for real coefficients. Okay, if there are no questions, I will go to abelian fourfolds. Okay, let me go to abelian fourfolds. Okay, so I'd like to discuss the result, so the standard conjecture of Hodge type holds for the variety A of dimension 4. Okay, let me give the proof. So first is this classical reduction to finite fields. Okay.
It's defined over some over what?
So here it's any field. Sorry.
Any number field.
It can be a number field, sure. But if it's in characteristic 0, then you can embed in C using singular cohomology, Hodge relations, and then it's known. So the interesting case is characteristic P.
But then how do you pass from number field to characteristic P?
So let me say it again. If it's in characteristic 0, the standard conjecture is well known for all varieties, because you can always embed in C, and then once you're in C, use singular cohomology, so you can understand signature there.
Yes, but I mean, which abelian? How do you pass from this abelian variety over number field over field of characteristic P?
You don't have to.
Not number.
Number field has a characteristic 0, so this case is well known.
But you're reducing it to characteristic.
He's talking about characteristic P.
Yeah,
So let me say,
okay.
the interesting case is characteristic P. That's what I'm saying. Okay, because characteristic 0 can be embedded in C. Okay. Okay, so let me explain why you can reduce over finite fields. Okay, and this argument would actually work also for number fields. So you can also follow this path, but it's much harder. So you take a variety, your abelian variety over any field. Sorry.
Who proved it in characteristic 0?
I mean, I think as soon as it was known to Grothendieck. I mean, as soon as you formulate the conjecture, it's clear that it works in characteristic 0. Okay, this was explained. Sorry. Here, that's the second case. Yeah, so this is classical. This was known. This was one of the evidence for Grothendieck. Yeah, as soon as you are in characteristic 0, you can take the class cycle map. You can embed in singular cohomology, and there you have positivity because of Hodge relations. Okay.
Is this map injective?
Yes, you can make it injective. This I also explained this. Yeah, say it's injective, and it's not 100% true, but you can go around.
I mean, this is a big problem. The compute gel group, it's not known for an abelian variety.
I'm thinking about algebraic classes.
Well,
All these questions is about algebraic classes, not about Chow groups. The intersection product are the what? Sorry, I can tell you. I can hear you. I can't hear you very well.
You're setting the image in which commodity theory?
If you take the algebra circles and you take the modulo by.
Yeah. So. Okay. Let me answer. So you have Chow groups.
Yes.
You go in some cohomology, p-adic or singular, whatever. Cycles, modulo homological equivalence. And the intersection product is compatible with the cup product. So you have no hope to have something non-degenerate if you work here. Here is very degenerate. So all the questions I was looking at about signature doesn't make sense. I mean, you have to look at here. And actually I'm looking at here. But it's a technical point. Because here we know unconditionally that it is non-degenerate. These two are conjecturally the same. Okay, and you can construct a section here and still talk about the class cycle map. Did I answer your question?
Not really, but you can go on.
Okay. You can ask again at the end if you want. Okay, so you can reduce to finite fields because you can always specialize. And you always have a specialization over a finite field. Once you have a specialization, then cycles injects into the specialization. So it's enough to work here. And now we are over finite field. We can use on that 8. And we know that this abelian variety lifts to C. And it's not just a lifting, it's a lifting to a CM abelian variety. And you can use the CM action to decompose the cohomology of the lifting or the abelian variety. And it's the decomposition of some subspaces which are semi-reductible. Yeah, so now you reduce your problem to these different smaller spaces. And now you fix one of those. And it turns out you can check that it fits in one of the following categories. One of the following. So either it is without algebraic classes, then of course it's not interesting for us. For the problem, I mean, either all algebraic classes are intersectional divisors. And in this case, I mean, it's not trivial, but you can reduce the divisors, and then you win again. And the very last, it's algebraic classes, not all coming from divisors. And that's the hard and new part. The point is that in case C, if you are in dimension 4, that's the only place where you use dimension 4, the rank of this cohomology group is 2. And now that you have something of rank 2, you are precisely in the same situation as in as for the Fermat cubic, as for the. So here you can apply the strategy in section 3. Okay, and we'll stop here. Thank you very much.
Yeah. Okay. Thanks, Giuseppe, very interesting talk. Any questions?
So I have a question. So in this step 4, I guess this is because VI is irreducible. So there's no case that some mixed case. You have some algebraic classes and also some transcendental cars. Is that true?
Yeah, exactly. Actually, either you don't have any class, either your cohomology group is spanned by class. And when it's spanned by class, either all of them are intersectional divisors, either none of them are intersectional divisors. Yes, it's an irreducibility argument, exactly.
Okay, so if I understand correctly, then your strategy is that you try to prove that somehow the two quadratic forms are different over C or over R, and then you try to use all other places like P and then you try to prove that for them, if P not to L, then they're the same, but P plus L is different, and from that you get
yeah, exactly. So
okay, I see.
Yeah, so sorry. Yeah, so you can imagine that you have a cup product over C and the intersection product over finite field, say. And yeah, the idea is exactly you look at the signature. Here, for example, you will have something negative. Then you have p-adic, and they are the same. And then you take over P, and they are different. Not the same. And once you understood this, but you can, using product formula, you deduce that it is positive.
Okay, so
I'm happy to come back to this question if the person can speak louder, and if he wants to.
Is this you know, there is a person called O'Sullivan in Australia.
Mm-hmm.
Is he the one that constructed this section of this map?
Yes. Yeah. So it turns out that in the CM case it's much easier, but indeed the way of so for this CM case I don't need this CM, which is actually a hard one, and this theorem is much harder because it's a section up to here. It's a much serious theorem. Sorry.
No, go on.
Yeah. So as I mean, so there are a lot of nice questions about these different subquotients, but somehow here in the case I'm looking at, you don't need all this sophisticated technology. It's everything is about the finite dimensional spaces and non-degenerate quadratic forms. Yeah, so I'm sorry.
You have to compute the image of the cycle map. This is kind of this is the Hodge conjecture. Compute the image of the cycle.
No, so I understand. You see, this is a very different conjecture from all the other ones. It's not about constructing cycles; it's about how they intersect. Yeah.
Yes, but
so
in order to compute this matrix, this quadratic form, you need to have a basis for these spaces of cycles.
Yes.
So you have to compute the basis for these spaces.
Yeah, I think the very simple the simplest example is this statement. You see, no one is saying that this row 1 is very big. The statement is just that this is the signature. Maybe row 1 is very small, and that's precisely what I'm showing. I'm not saying that there are a lot of cycles. I'm not able to. I mean, I think nobody's able to say something like this. I'm just saying how they intersect.
This is okay. Yeah. So you
Okay.
are not able to compute these two.
No, and in the proof here, so you have these different three classes, three cases, and of course I'm not able to say how often these cases happen. Yeah, so I'm not able to say, okay, this is very frequent, or there are a lot of, or always, as soon as you have a Frobenius invariant class, you will have algebraic cycles. Of course, I'm not saying this. I'm just saying is if you are in one of these cases, okay, then they intersect positively. Okay.
So if I understand, then here you need the assumption the rank equals 2, because somehow you can say if a matrix is positively definite by in rank 2, somehow by completing the determinant, and the determinant just numbers, so you can multiply.
Exactly. Yeah. So the signature is determined by the discriminant and the Hilbert symbol. And this is true only in Hilbert symbol, and this is true only in rank 2. Oh, sorry. In rank 2. Okay, that's why I need rank 2.
Thank you. Any other questions? So we still have a lot of, I think several more minutes. So if one wants to ask questions. Okay, so if not, then thanks Giuseppe again, and then we will resume after 12.
Yeah, thank you very much.